if I gave you an oracle that was able to do some aspect of what you do, and you could just collaborate with it.
Yeah.
What would you like that oracle to be able to do? Would you like it to maybe be a verifier, like check,
Mhm.
do the codes, yes,
Yeah.
Professor Tao, this is a promising, fruitful direction.
Yeah.
Or would you like it to generate possible proofs, and then you see which one is the
Mhm.
right one? Or would you like it to maybe generate different representation, totally different ways of seeing this problem?
Yeah. I think all of the above. A lot of it is we don't know how to use these tools because it's a paradigm that it's not. Um, yeah, we have not had in the past assistants that are competent enough to understand complex instructions
Mhm.
that can work at massive scale, but are also unreliable. Like it's an interesting, but unreliable in subtle ways, was providing sufficiently good output. It's a interesting combination. I mean, you have like graduate students that you work with who kind of like this, but not at scale. And we had previous software tools that can work at scale, but very narrow. So we have to figure out how to use. So Tim Gallagher actually, I mean, you imagine he actually foresaw, like in 2000, he was envisioning what mathematics would look like in actually 2.5 decades. And
That's funny.
yeah, he wrote in his article a hypothetical conversation between a mathematical assistant of the future and himself. He's trying to solve a problem, and they would have a conversation. Sometimes the human would propose an idea, and the AI would evaluate it. And sometimes the AI would propose an idea, and sometimes a computation was required, and the AI would just go and say, "Okay, I've checked the 100 cases needed here," or the first you said this is true for all n. I've checked it for n up to 100, and it looks good so far. Or hang on, there's a problem at n equals 46. And so just a free-form conversation where you don't know in advance where things are going to go, but just based on I think ideas get proposed on both sides, calculations get proposed on both sides. I've had conversations with AI where I say, okay, we're going to collaborate to solve this math problem, and it's a problem that I already know the solution to. So I try to prompt it. Okay, so here's the problem. I suggest using this tool, and it'll find this lovely argument using a completely different tool, which eventually goes into the weeds and say, no, try using this. Okay, and it might start using this, and then it'll go back to the tool that I wanted to do before. And like you have to keep railroading it onto the path you want. And I could eventually force it to give the proof I wanted, but it was like herding cats. And the amount of personal effort I had to take to not just sort of prompt it, but also check its output, because a lot of what it looked like it's going to work. But oh no, there's a problem on line 17, and basically arguing with it. Like it was more exhausting than doing it unassisted. So but that's the current state of the art.
I wonder if there's a phase shift that happens to where it's no longer feels like herding cats, and maybe you'll surprise us how quickly that comes.
I believe so. So in formalization, I mentioned before that it takes 10 times longer to formalize a proof than to write it by hand. With these modern AI tools, and also just better tooling, the lean developers are doing a great job adding more and more features and making it user-friendly. It's going from 9 to 8 to 7. Okay, no big deal. But one day it will drop below 1. And that's the phase shift. Because suddenly it makes sense when you write a paper to write it in lean first, or through a conversation with AI who is generating lean on the fly with you. And it becomes natural for journals to accept, maybe they'll offer expedite refereeing. That if a paper has already been formalized in lean, they'll just ask the referee to comment on the significance of the results and how it connects to literature, and not worry so much about the correctness because that's been certified. papers are getting longer and longer in mathematics, and like it's harder and harder to get good refereeing for the really long ones, unless they're really important. It is actually an issue which, and the formalization is coming in at just the right time for this to be.
And easier and easier to guess because of the tooling and all the other factors,
Right.
then you're going to see much more like math lib will grow
Right.
potentially exponentially.
Yeah.
It's a virtuous cycle. Okay.
I mean, one phase shift of this type that happened in the past was the adoption of LaTeX.
Mhm.
So LaTeX is this typesetting language that all mathematicians use now. So in the past, people used all kinds of word processors and typewriters and whatever. But at some point, LaTeX became easier to use than all other competitors, and that people would switch, within a few years. Like it was just a dramatic phase shift.
It's a wild out there question, but what year? How far away are we from a AI system being a collaborator on a proof that wins the Fields medal? So that level.
Okay. Well, it depends on the level of collaboration. I mean,
No, like it deserves to
Right.
get the Fields medal. Like, so half
Okay.
and half.
Already, like I could imagine if it was a medal winning paper having some AI assistance in writing it, like the autocomplete alone is already, I use it, like it speeds up my own writing. Like, you can have a theorem, and you have a proof, and the proof has three cases. And I write down the proof of the first case, and the autocomplete just suggests, sorry, now here's how the proof of the second case could work. And like it was exactly correct. That was great. Saved me like 5-10 minutes of typing.
But in that case, the AI system doesn't get the Fields medal.
No.
Are we talking 20 years, 50 years, 100 years? What do you think?
Okay. So I gave a prediction in print, but so by 2026, which is now next year, there will be math collaborations, with AI. So not Fields medal winning, but like actual research level math papers.
Like published ideas that are in part generated by AI.
Maybe not the ideas, but at least some of the computations, the verifications. Yeah, I mean,
Has that already happened?
Has already happened. Yeah, there are problems that were solved by a complicated process, conversing with AI to propose things, and the human goes and tries it, and they kind of like doesn't work. But if I propose a different idea, it's hard to disentangle exactly. There are certainly math results which could only have been accomplished because there was a human mathematician and an AI involved. But it's hard to sort of disentangle credit. I mean, these tools, they do not replicate all the skills needed to do mathematics, but they can replicate sort of some non-trivial percentage of them, 30, 40%. So they can fill in gaps. So coding is a good example. So it's annoying for me to code in Python. I'm not a native, I'm not a professional programmer. But with AI, the friction cost of doing it is much reduced. So it fills in that gap for me. AI is getting quite good at literature review. I mean, there's still a problem with hallucinating, the references that don't exist. But this, I think, is a solvable problem. If you train in the right way and so forth, you can and verify, using the internet. You should in a few years get to the point where you have a lemma that you need, and say, has anyone proven this lemma before? And it will do basically a fancy web search AI assistant and say, yeah, there are these 6 papers where something similar has happened. And I mean, you can ask it right now, and it will give you 6 papers, of which maybe 1 is legitimate and relevant, 1 exists but is not relevant, and 4 are hallucinated. It has a non-zero success rate right now, but there's so much garbage, the signal to noise ratio is so poor that it's most helpful when you already somewhat know the literature, and you just need to be prompted to be reminded of a paper that was already subconsciously in your memory.
Versus helping you discover you were not even aware of, but is the correct citation.
Yeah, that's Yeah, that it can sometimes do, but when it does, it's buried in a list of options for which the other
that are bad.
Yeah,
I mean, being able to automatically generate a related work section that is correct.
Yeah.
That's actually a beautiful thing that might be another phase shift because it assigns credit correctly.
yeah,
It does. It breaks you out of the silos of
yeah. No, I mean,
thought.
yeah, no, but there's a big hump to overcome right now. I mean, it's like self-driving cars.
Right.
The safety margin has to be really high
Yeah.
for it to be feasible. So yeah, so there's a last mile problem with a lot of AI applications that they can develop tools that work 20%, 80% of the time, but it's still not good enough, and in fact, even worse than good in some ways.
I mean, another way of asking the Fields Medal question is, what year do you think you'll wake up and be like real surprised? You read the headline, the news of something happened that AI did, like, real breakthrough, something. It doesn't, like Fields Medal, the Riemann Hypothesis. It could be like really just this alpha zero moment would go, that kind of thing.
Right. Yeah, this decade, I can see it like making a conjecture between two things that people thought was unrelated.
Oh, interesting. Generating a conjecture that's a beautiful conjecture.
Yeah, and actually has a real chance of being correct and meaningful. And
because that's actually kind of doable, I suppose. But where the data is,
yeah.
No, that would be
Well,
truly
it's
amazing. Yeah.
the current models struggle a lot. I mean, so a version of this is, I mean, the physicists have a dream of getting the AI to discover new laws of physics. The dream is you just feed it all this data, okay, and this is here's a new patent that we didn't see before. But it actually even struggles. The current state of the art even struggles to discover old laws of physics from the data. I mean, or if it does, there's a big concern of contamination. That it did it only because, like, somewhere in this training data, it already somehow knew, Boyle's law or whatever law you're trying to reconstruct. Part of it is that we don't have the right type of training data for this. So for laws of physics, like we don't have like a million different universes with a million different laws of nature. Like a lot of what we're missing in math is actually the negative space of. So we have published things that people have been able to prove, and conjectures that ended up being verified, or maybe counterexamples produced. But we don't have data on things that were proposed, and they're kind of a good thing to try. But then people quickly realized that it was the wrong conjecture, and then they said, "Oh, but we should actually change our claim to modify it in this way to actually make it more plausible." There's a trial and error process, which is a real integral part of human mathematical discovery, which we don't record because it's embarrassing. We make mistakes, and we only like to publish our wins. And the AI has no access to this data to train on. I sometimes joke that basically the AI has to go through a grad school and actually, go to grad courses, do the assignments, go to office hours, make mistakes, get advice on how to correct the mistakes, and learn from that.
Let me ask you, if I may, about Grigori Perelman.
Mhm.
You mentioned that you try to be careful in your work and not let a problem completely consume you. Just you really fall in love with the problem and really cannot rest until you solve it. But you also hasted to add that sometimes this approach actually can be very successful.
Mhm.
And the example you gave is Grigori Perelman, who proved the Poincare conjecture and did so by working alone for 7 years with basically little contact with the outside world. Can you explain this one Millennium Prize problem that's been solved, Poincare conjecture, and maybe speak to the journey that Grigori Perelman's been on?
All right, so it's a question about curved spaces. Earth is a good example. So Earth, you can think of as a 2D surface. In addition to being round, the Earth could maybe be a torus with a hole in it, or it could have many holes. And there are many different topologies a priori that a surface could have, even if you assume that it's bounded and smooth and so forth. So we have figured out how to classify surfaces. As a first approximation, everything's determined by something called the genus, how many holes it has. So a sphere has genus 0, a donut has genus 1, and so forth. And one way you can tell these surfaces apart, probably the sphere has, which is called simply connected. If you take any closed loop on the sphere, like a big closed loop rope, you can contract it to a point and while staying on the surface. And the sphere has this property, but a torus doesn't. If you're on a torus and you take a rope that goes around, say, the outer diameter of the torus, there's no way, it can't get through the hole. There's no way to contract it to a point. So it turns out that the sphere is the only surface with this property of contractibility, I mean, up to like continuous deformations of the sphere. So things that are what are called topologically equivalent of the sphere. So Poincaré asks the same question in higher dimensions. So it becomes hard to visualize because surface you can think of as embedded in 3 dimensions, but a curved free space, we don't have good intuition of 4D space to live in. And then there are also 3D spaces that can't even fit into 4 dimensions. You need 5 or 6 or higher. But anyway, mathematically, you can still pose this question, that if you have a bounded 3-dimensional space now, which also has this simply connected property, that every loop can be contracted, can you turn it into a 3-dimensional version of a sphere? And so this is the Poincaré conjecture. Weirdly, in higher dimensions, 4 and 5, it was actually easier. So it was solved first in higher dimensions. There's somehow more room to do the deformation. It's easier to move things around to be a sphere. But 3 was really hard. So people tried many approaches. There's sort of combinatorial approaches where you chop up the surface into little triangles or tetrahedra, and you just try to argue based on how the faces interact with each other. There were algebraic approaches. There's various algebraic objects, like things called the fundamental group, that you can attach to these homology and cohomology and all these very fancy tools. They also didn't quite work. But Richard Hamilton's proposed a partial differential equations approach. So you take so the problem is that you have this object which is sort of secretly is a sphere, but it's given to you in a really in a weird way. So it's like I think of a ball that's been kind of crumpled up and twisted, and it's not obvious that it's a ball. But like if you have some sort of surface which is a deformed sphere, you could for example, think of it as the surface of a balloon. You could try to inflate it. You blow it up, and naturally, as you fill it with air, the wrinkles will sort of smooth out, and it will turn into a nice round sphere. Unless, of course, it was a torus or something, in which case it would get stuck at some point. Like if you inflate a torus, there'd be a point in the middle. When the inner ring shrinks to 0, you get a singularity, and you can't blow up any further. You can't flow any further. So he created this flow, which is now called Ricci flow, which is a way of taking an arbitrary surface or space and smoothing it out to make it rounder and rounder, to make it look like a sphere. And he wanted to show that either this process would give you a sphere or it would create a singularity. Actually, very much like how PDEs either they have global regularity or finite time blow up. Actually, it basically is almost exactly the same thing. It's all connected. And he showed that for 2-dimensional surfaces, if you started simply connected, no singularities ever formed. You never ran into trouble, and you could flow, and it would give you a sphere. And so he got a new proof of the 2-dimensional result.
But by the way, that's a beautiful explanation of Ricci flow and its application in this context. How difficult is the mathematics here, like for the 2D case? Is it?
Yeah, these are quite sophisticated equations on par with the Einstein equations. Slightly simpler, but but they were considered hard nonlinear equations to solve. And there's lots of special tricks in 2D that helped. But in 3D, the problem was that this equation was actually supercritical. It has the same problem as Navier-Stokes. As you blow up, maybe the curvature could get concentrated in finer, smaller regions, and it looked more and more nonlinear, and things just looked worse and worse. And there could be all kinds of singularities that showed up. Some singularities, like if there's these things called neck pinches, where the surface sort of behaves like a barbell, and it pinches at a point. Some singularities are simple enough that you can sort of see what to do next. You just make a snip, and then you can turn one surface into 2 and evolve them separately. But there was the prospect that some really nasty, like knotted singularities showed up that you couldn't see how to resolve in any way, that you couldn't do any surgery to. So you need to classify all the singularities, like what are all the possible ways that things can go wrong. So what Perlman did was, first of all, he turned the problem from a supercritical problem to a critical problem. I said before about how the invention of energy, the Hamiltonian, like really clarified Newtonian mechanics. So he introduced something which is now called Perlman's reduced volume and Perlman's entropy. He introduced new quantities, kind of like energy, that looked the same at every single scale, and turned the problem into a critical one where the nonlinearities actually suddenly looked a lot less scary than they did before. And then he still had to analyze the singularities of this critical problem. And that itself was a problem similar to this wave math thing I worked on, actually. So on the level of difficulty of that, so he managed to classify all the singularities of this problem and show how to apply surgery to each of these, and through that was able to resolve the Poincare conjecture. So quite like a lot of really ambitious steps, and like nothing that a large language model today, for example, could. I mean, at best, I could imagine a model proposing this idea as one of hundreds of different things to try. But the other 99 would be complete dead ends, but you'd only find out after months of work. He must have had some sense that this was the right track to pursue, because it takes years to get them from A to B.
So you've done, like you said, actually, you see, even strictly mathematically, but more broadly in terms of the process, you've done similarly difficult things. What can you infer from the process he was going through? Because he was doing it alone. What are some low points in a process like that when you start to, you've mentioned hardship, AI doesn't know when it's failing. What happens to you? You're sitting in your office when you realize the thing you did for the last few days, maybe weeks, is a failure.
Well, for me, I switched to a different problem. So I'm a fox. I'm not a hedgehog.
But you legitimately, that is a break that you can take, is to step away and look at a different problem.
Yeah. You can modify the problem too. You can add some cheat. If there's a specific thing that's blocking you, that this some bad case keeps showing up that for which your tool doesn't work, you can just assume by fiat this bad case doesn't occur. So you do some magical thinking, but strategically, for the point to see if the rest of the argument goes through. If there's multiple problems with your approach, then maybe you just give up. Okay, but if this is the only problem and everything else checks out, then it's still worth fighting. So you have to do some sort of forward reconnaissance sometimes to,
And that is sometimes productive to assume, okay, we'll figure it out.
Oh yeah.
Eventually.
Sometimes actually it's even productive to make mistakes. So one of the, there was a project which actually we won some prizes for. Actually, with 4 other people. We worked on this PD problem. Again, actually, this blow of regularity type problem. And it was considered very hard. Jean Bourgain, who was another fields methodist who worked on a special case of this, but he could not solve the general case. And we worked on this problem for 2 months, and we thought we solved it. We had this cute argument that if everything fit, and we were excited. We were planning celebrationary to all get together and have champagne or something. And we started writing it up. And one of us, not me actually, but another co-author, said, in this lemma here, we have to estimate these 13 terms that show up in this expansion, and we estimate 12 of them, but in our notes I can't find the estimation of the 13th. Can someone supply that? And I said, sure, I'll look at this, and actually, we didn't cover it. We completely omitted this term, and this term turned out to be worse than the other 12 terms put together. In fact, we could not estimate this term. And we tried for a few more months and all different permutations, and there was always this one term that we could not control. And so this was very frustrating. But because we had already invested months and months of effort in this already, we stuck at this. We tried increasingly desperate things and crazy things. And after 2 years, we found an approach which was somewhat different, by quite a bit from our initial strategy, which didn't generate these problematic terms and actually solve the problem. So we solved the problem after 2 years. But if we hadn't had that initial false dawn of nearly solving the problem, we would have given up by month 2 or something and worked on an easier problem. If we had known it would take 2 years, not sure we would have started the project. Yeah, sometimes actually having the incorrect, it's like Columbus traveling the New World. They had an incorrect version of the measurement of the size of the Earth. He thought he was going to find a new trade route to India. Or at least that was how he sold it in his prospectus. I mean, it could be that he actually secretly knew, but
just on the psychological element, do you have like emotional or like self-doubt that just overwhelms you, moments like that? Because this stuff, it feels like math is so engrossing that like it can break you when you like invest so much yourself in the problem and then it turns out wrong. You could start to, a similar way chess has broken some people.
Yeah, I think different mathematicians have different levels of emotional investment in what they do. I mean, I think for some people it's as a job. You have a problem, and if it doesn't work out, you go on the next one. So the fact that you can always move on to another problem, it reduces the emotional connection. I mean, there are cases, so there are certain problems that are what are called mathematical diseases, where just latch on to that one problem and they spend years and years thinking about nothing but that one problem, and maybe their career suffers and so forth. They say, "Oh, but okay, this big win. This will, once I finish this problem, that will make up for all the years of lost opportunity." And that's. I mean, occasionally it works, but I really don't recommend it for people who have the right fortitude. Yeah, so I've never been super invested in any one problem. One thing that helps is that we don't need to call our problems in advance. When we do grant proposals, we sort of say we will study this set of problems. But even there, we don't promise definitely by 5 years I will supply a proof of all these things. You promise to make some progress or discover some interesting phenomena. And maybe you don't solve the problem, but you find some related problem that you can say something new about, and that's a much more feasible task.
But I'm sure for you, there's problems like this. You have made so much progress towards the hardest problems in the history of mathematics. So, is there a problem that just haunts you? It sits there in the dark corners, twin prime conjecture, Riemann hypothesis, Goldbach conjecture.
Twin prime, that sounds, well, again, so I mean, the problems like the Riemann hypothesis, those are so far out of reach.
Do you think so?
Yeah, there's no even viable strategy. Like, even if I activate all the cheats that I know of in this problem, like there's just still no way to get from A to B.
Yeah.
I think it needs a breakthrough in another area of mathematics to happen first, and for someone to recognize that it would be a useful thing to transport into this problem.
So we should maybe step back for a little bit and just talk about prime numbers.
Okay.
So they're often referred to as the atoms of mathematics. Can you just speak to the structure that these atoms provide?
So the natural numbers have two basic operations attached to them: addition and multiplication. So if you want to generate the natural numbers, you can do one of two things. You can just start with 1 and add 1 to itself over and over again, and that generates you the natural numbers. So additively, they're very easy to generate: 1, 2, 3, 4, 5. Or you can take the prime number. If you want to generate multiplicatively, you can take all the prime numbers, 2, 3, 5, 7, and multiply them all together. And together, that gives you all the natural numbers, except maybe for 1. So there are these two separate ways of thinking about the natural numbers from an additive point of view and a multiplicative point of view. And separately, they're not so bad. So like any question about that natural numbers that only was addition is relatively easy to solve. And any question that only was multiplication is relatively easy to solve. But what has been frustrating is that you combine the two together, and suddenly you get an extremely rich. I mean, we know that there are statements in number theory that are actually as undecidable. There are certain polynomials in some number of variables. Is there a solution in the natural numbers? And the answer depends on an undecidable statement, like whether the axioms of mathematics are consistent or not.